Today I want to talk about this study, gold nugget formation from earthquake-induced piezoelectricity in quartz. And the TLDR is that researchers were able to get gold flakes to form on quartz crystals in the lab by inducing earthquake-like vibration. And if that's all you wanted to know, hit the like on the way out. It was nice seeing you, and I'll catch you next time. Otherwise, let's go a little deeper. This rock is made up of quartz, and you have native gold attached to it. That's basically flakes of pure gold that are stuck to different crystals on this rock of quartz. So in a pure silicon crystal, it's made up exclusively of silicon and oxygen, and they form up in these little patterns here. In this case, the oxygen is represented by the white balls and the silicon by the red ones, but it really doesn't matter too much which is which for visualizing the structure. When quartz cools very slowly, you can get these nice, very clean, kind of oblong crystals. And when you see quartz that's rose-colored or purple or whatever other color, it's because of impurities within the crystal, so other elements that have gotten in there. Quartz is an insulating material. It doesn't conduct electricity really at all. It's also a piezoelectric material, which means that when an alternating current is applied to a crystal of quartz, it creates a vibration. And that vibration is very predictable based on the purity of the crystal and its shape and size. And back in the day, vibration standards were actually set by quartz crystals that had an electric current applied to them. And these are standards that were used by different companies in the 50s. Well, this one's from 32. A second property of piezoelectric materials is when a force is applied to them, it causes the atoms within the crystal structure to realign so that one side of that crystal can become more positive and the other can become more negative. So you can see in these theoretical drawings, when force is applied to the top and the bottom of the crystal, the negative charges line up by the top and the positive charges by the bottom. When force is applied from the sides, the direction of that charge shifts. So even though electricity doesn't move through the material, one side can have more affinity to positive charge and the other side can have more affinity to negative, and it can switch. So now let's talk about where the gold comes from. This is one tectonic plate. This would be a crustal plate, and it's going under another. And this is actually what happens when you have mountain building, like is going on in the Rocky Mountains right now. The Pacific plate is getting pushed under the North American continental plate. When that happens, as that plate that's subducting goes toward the Earth's mantle, it gets hotter and hotter and it begins to melt. So you basically get these pools of magma that are rich in metals and minerals to start welling up toward the surface. They're basically in a liquid form, so they start moving up. Well, eventually they run into groundwater, and that groundwater is instantly converted into steam. That groundwater is also holding a lot of elements itself, including things like sulfur and chloride. Well, that super hot steam starts to crack the rock that water is moving through. So you wind up with these cracks and fissures that run up through the rock all the way toward the surface. And you can see that at the top, that steam escapes through hot springs, kind of like you would see in Yellowstone, for example. Well, the way the gold gets dissolved is by attaching on to these hydrogen sulfide ions. And it forms this complex ion, AuHs2. Au is the periodic table symbol for gold. So wherever you see Au, understand it's referring to gold. And basically what these folks are saying is that gold gets transported up, dissolved in water, and as that water gets to the top, the gold is released, and you get H2S, which then goes up with that steam and escapes through those hot springs. And the gold is deposited as native metal, as nuggets and flakes. Well, the interesting thing about that is the gold doesn't just attach to any rock. It attaches very preferentially to quartz. This is a gold vein actually going through a large quartz deposit. So it's a pretty good question, why is this happening? Well, what the researchers in this study proposed is that quartz, through the piezoelectric effect, is catalyzing these gold-containing ions to break apart and then causing those little gold nanoparticles to deposit onto the quartz itself. And because gold is such an excellent conductor, you can just get more and more of those nanoparticles piling on in layers. So specifically what they looked at was 3 different reactions that can occur within the Earth's crust that basically bring gold out of solution. So here's the one I was talking about earlier, that AuHS2. You can also have this one where it's just one HS complex that's attached. And you can have this one where it's basically gold tetrachloride. It's gold with 4 chloride ions attached to it. Over here, you can see the different energies of reaction. And you can see this one at the top has the biggest number. So what they figured was, if they can make this reaction happen, then these reactions that actually require less energy would be proven to happen as well. Now, just to give you an idea of how much gold would be in that water that's coming up from below the surface of the Earth, it would be about 1 part per billion. So in order to get one little flake of gold, you need the equivalent of about 5 Olympic swimming pools of water. And this is a diagram of the molecule they tested, so this should give you an idea of how it would be shaped. This was their experimental apparatus. They got some chunks of quartz, very small quartz slabs. You can see 2 centimeters by 1 centimeter by half a centimeter thick, so very small, not even an inch across. They had that little piece of quartz sitting in this miniature tub with their gold solution. And then they had this little motor here that basically pushed on it and created an earthquake-like scenario. Now, what they noted is that large earthquakes generally have frequencies between 0.1 and 10 hertz, so 10 cycles per second, and smaller earthquakes have between 5 and 60 hertz. So they decided to run their apparatus at 20 hertz, so somewhere right in the middle. They got the pieces of quartz they used from the Victoria gold fields, which I guess there was a huge gold boom there in Australia about 150 years ago. And just getting back to this image, what they figured was going to happen was when they applied that vibration, it was going to catalyze the reactions around this quartz crystal that were going to allow those molecules to break down and cause gold, to start attaching to the sides of the quartz. So this is from one of their naked pieces of quartz that didn't have any gold already starting to deposit on it. And you can see on here, there are all these gold nanoparticles that are beginning to attach onto the quartz, and some of them are even starting to form small crystals. Now, these are very, very small. I mean, we're looking at crystals that are barely even a micron across. And this is from a slab of quartz that already had some gold naturally beginning to form on it. And you can see that they were able to attach additional nanoparticles of gold onto the quartz. And here are some more pictures of those nanocrystals. I think they're just so cool. No experiment would be complete without a control, so this is just a slab of quartz that they applied no vibration to. And as you can see, there are no crystals forming. I thought this was an awesome study and an insanely good proof of concept.